So in 7.1, let's remind ourselves that if we have a function f of x, if we want to find the area between that function and the x-axis, let's say from A to B, then when we originally did that, we looked at drawing some little small rectangles. And we found the area of those rectangles by taking their height, which their heights were given by the y value, which is our f of x, times the width, and we added those up. And we saw that as we got more and more of those rectangles, and the width got smaller and smaller, that approached the exact area in this region. But when we did that, that took 11 years to do that problem in about 3 pages. And we later discovered that we can write that as a definite integral from the left endpoint to the right endpoint of our function dx. And the way we evaluate that definite integral is we get the antiderivative we substitute in the right endpoint, we substitute in the left endpoint, and we take the difference. And as a way of thinking about it, you can think of an integral as what we're doing. As we go from A to B, we're just accumulating more and more area as we go. The only thing is we're accumulating the exact area instead of just some approximation. One place we ran into trouble, though, was that if our function was not positive, if our function was negative over our interval, then when we accumulated our area as we went across, since basically what we had done was, in a sense, add up these little rectangles, and the height of those rectangles were given by that y value. If that y value is negative, well, our delta x, that's positive. When we do our y times our delta x, negative times positive gave us a negative value for each of those areas. Which, if the function is always negative, that's not a huge deal, because if we were to integrate that function from A to B, if all of those were negative, then they would accumulate, and we would have a negative value, but that value would be the area between A and B. But where it really got bad is where our function was sometimes positive, sometimes negative. Because if we did that integral, since what that integral really represents is the accumulation of our f of x delta x's as we go from A to B, some of those areas or some of those rectangles are going to be negative areas. Some of those are going to be positive areas. And if we just add those up, some of these negatives are going to cancel with some of those positives. So the value that we get for that definite integral is not actually even going to be remotely close to what the area is if we consider our area this area plus this area. And we didn't really work hardly any problems like this, but what we discussed in class that we could kind of overcome this problem by saying, let's find where the x-intercept of our function is. And we could actually break this into two different integrals. We can integrate from our left side to that middle of our function. But keep in mind that's going to be a negative value because each of those little infinitely small rectangles is going to have a negative area. So to make that area positive, multiply that by a negative. So that would give us that area, and then we could add to that this area, which we could get from integrating from C to B that same function. So the trick there is just finding out, well, where does our function go from being negative to being positive? So with the understanding that basically when we integrate our function that it gives us the area of those rectangles, we can do lots of different things with that. 7.1 is going to have us use that to find, instead of just the area of a single curve, to find the area between multiple curves. We have this function f and some other function g that's a completely different function. We can get the area between f and g over a particular interval. So we can get this area if we want, if we're clever. Now, if we integrate from a to b f, if we integrate f from a to b, that gives us the area between f of x and the x-axis. Well, notice that has some extra stuff in there. That extra stuff is all of this. But how could I find what that area is? Yeah, if we think about a small rectangle that goes from the x-axis to that area is given by g of x, the height, g of x times its width. So if we add all those up, we would be integrating from a to b g of x. So that would be that area. So when we integrate f of x, it gives us our area from here to the x-axis. When we integrate g of x, it gives us the area from here to the x-axis. So how do we get this area that we want? Yeah, subtract those. If we were to take this away, that would give us that area. So we're just simply going to subtract those. So if we want the area between two curves, we're going to integrate from our left to our right side. It'll always, they might have different names. This one might be called G, this one might be called F, or this one might be called V and this one U. But we're always going to do our top function minus the bottom function. And that'll give us the area between the curves. Well, it might have crossed your mind, well, that's all good and well the way you have it drawn, but what if g of x is below the x-axis? Didn't we have problems there? And when we have a single function, we do. But let's look. Let's suppose that's g and f. We'll just call that one f, this one g. And let's just draw a sample rectangle. So let's see if f minus g is really going to give us that distance, because when we integrate, remember that this part represents the width of our rectangle in a sense. This part represents the length of our rectangle. And then we're just, definite integral says we're adding all those up from the left to the right. So we need to see if f minus g really is going to give us that length. Well, let's use this particular value. What is f here? What is the y value here? 6. What is the y value here? -4. So if we take f minus g, you get 10. Well, that's really how long that is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So while we do, when we have a single curve, have to worry about, well, is our function above or below the x-axis? When we have two functions, as long as we do the top function minus the bottom function, that will account for whatever. That's when we do f minus g, that's finding the distance from f to g. It doesn't matter if f is positive, g is negative, f is negative, g is negative, it doesn't matter. Anytime you take two values and subtract them, it's finding the distance between them, as long as you take the larger minus the smaller. You can illustrate that's even true if both values are negative. We have f and g. If we think about a sample rectangle right here, our y value here is -1. Our y value here, let's call that -7. If we take our f minus our g, notice we get 6, which is that distance. 1, 2, 3, 4, 5, 6. So as long as we do our top minus our bottom function, that will give us the area between those curves. So let's look at an example. Let me pull up our book so we can have these pictures. All right, let's work one of these. Let's take, we'll just look at number 3. I know that's an odd one, but this. So if we want to look at these, we have two different curves. We have y1 describes the bold curve, y2 describes the lighter one. So if we want to describe that area, toolbar on the side. My main toolbar has disappeared. All right, let's copy this. Then the area between those curves we can get from integrating from our left side to our right side. Our top function minus the bottom one. So how far to the left is our left side? What would you say our x value here is? 0. And how far to the right does it go? 3. Our top function is negative x squared plus 2x plus 3. Our bottom function, that's y1, so x squared minus 4x plus 3 dx. So the integral from 0 to 3, we have a negative x squared minus an x squared, so minus 2x squared, that takes care of those. We have a 2x minus a negative, so plus 4x, so plus 6x. And then we have a 3 minus a 3, which is 0. So that's the integral that will give us the area between those. And if we did pick the correct function to be the top one and the correct one for the bottom one, then when we integrate that, we should get a positive value for that area. So let's do that. We want to solve this. To integrate this, we do x to the 1 greater power over that power. This one, x to the 1 greater power over that power, and we're going to evaluate that from 0 to 3. Now, of course, the 6 and the 2 reduce. So if we substitute a 3 in, we have negative 2 is 3 cubed over 3 plus 3 times 3 squared. If we substitute a 0 in, what do we get for this term? 0. And if we substitute a 0 in, what do we get for this term? 0. Be careful. Okay, sometimes when you substitute a 0 in, you don't get a result of 0 for that. Sometimes you do, but you don't always just assume, well, if I plug a 0 in, I'm going to get zeros. Depends on what your integral is. All right, so if we do this, 3 cubed, that's 27 times negative 2, so negative 54 over 3. 3 squared, that's 9 times 3, so 27, which we need a common denominator. Multiply top and bottom by 3. So negative 54 over 3. It's at 81 over 3. It's at 27 over 3, or 9. So it turns out for that particular region, that exact area between those two curves is 9. Let's look at number 6. We're not going to completely work it out, but let's just look at how you would set this up. Is the same function on top the whole time? No. Notice for this section, see, they're calling the bold one Y1, and then the light one Y2. So for this section, Y1 is on top. For this section, Y2 is on top. So in order to get that area, we actually have to do two different integrals. For this one, we integrate from the left side to here, so from 0 to 1, our top function minus our bottom function. Then for this region, we integrate from here to here, so from 1 to 2. Still our top function, but now our top function is Y2. So if we want the area between those curves, we have to take those two and add them up. So we can't just say, well, we're going to go from 0 to 2, Y1 minus Y2, because Y1 is not always on top, Y2 is not always on top. So we have to do that in particular regions. Now they said, we're not going to work this one out, but they've been nice to us on this problem in that they gave us a graph. But if they just gave us the functions, which y1 is x minus 1 cubed, y2 is x minus 1, and they said to find the area between the two curves, it's a little bit more challenging because then we have to think, well, what do our curves look like? Which it's nice if you have a graphing calculator because you can plot these. And it's good to make a sketch of them. It's not necessarily a requirement to make a sketch, but this one is a straight line with a y-intercept of -1. This one is a cubic equation which does this number. So I'm just going to make a rough sketch, and in fact, let me take the axis out. Our function is probably going to do something like that, which we know, yeah, it does something like that. So the question is, where are those points? Because since we have to do that as two different integrals, if we call this A, B, and C, we have to know what A and B are, B and C, to do those integrals. Well, if I have two functions and I want to find out these points, how do I do that? How do I find where 2 points intersect, or two equations like that intersect? They intersect where they're equal. So if we want to find these points of intersection, we want to find out when that's equal to that. if we add functions, let's say x squared and qx plus 3, if we want to find out where those functions intersect, y equals x squared, that's a parabola. 2x plus 3, that's a straight line. So if we're looking for that area, we need to find out, well, where are those points of intersection, so we'll know where to start and stop our integral. Well, they intersect where our functions are equal. If you think about it, at this point, this is f, this is g. At that point, f and g have the same y value. They're equal there. Here, y is the same for this function and for that function. So if we set those functions equal and solve, that'll give us our edges. How will we solve this equation? Set it equal to 0. Factor. Set those equal to 0, so we get 3 and negative 1. Those are our points of intersection. So here, our x is negative 1. Here, our x is 3. Now, I drew this for you, so you know from looking at it which function's on top. Which one is on top, G or F? G. This is G, this is F. So to get our area, we go from negative 1, the left side, to 3, the right side. We do the top function minus the bottom function. We can do that without a picture, though. If I were to come in here, and I were to get rid of that picture, we know that we're going to integrate from negative 1 to 3. The question is, which function is on top? Here, our functions intersect. So in between here, one function is above the other. So the way we determine is which y value is greater than the other one. What would be an x value in between here? 0. Well, for this function, when x is 0, y 0. So when x is 0, y is 0 for that function. For our other function, when x is 0, what is y? 3. So just looking at that part, which would you say is the top function, which is the bottom? Yeah. That y value is above that y value, so that one's the top one. That one's the bottom. If we look back at that previous problem where they call it y1 and y2, I'll call it f of x and g of x. And we found that there were 3 points of intersection, and they plotted those on the graph, 0, 1, and 2. So if we want to decide, okay, in this first interval, which one is on top? What would be a test point in this interval? A half. If we put a half into this function, we can just do that in our calculator. 0.5 minus 1 is negative 0.5, and then if we cube that, negative 0.125. If we substitute that same x value into the other function, 0.5 minus 1, we get negative 0.5. So which one of these would you say is above the other? F. The one that has the larger y value is the top one. This is the larger y value. If you think about this being 0, 1, 2, negative 1, negative 2. Remember, as for negative numbers, the larger the number is for a negative, the lower it is. This has the larger quantity, but it's negative. So that's more negative than that, so that's your larger value. Just think about it. When I describe in basic math, I would rather owe somebody $0.125 than owe them $0.5. So that top one is larger. So that's the top function in that region. In this region, we could use the test point 1.5. If we put a 1.5 in to F, 1.5 minus 1, and cube it, we get 0.125. If we put that same test point into G, we get 0.5. So which one of those is on top? G. So if we set up our integral, we would go from 0 to 1, and we would do f minus g. And then our second interval goes from 1 to 2, and in that region, g is the top function.
Where did you get the 0, 1,
Those, that was the one where they gave us the picture. Those were our points of intersection. Yeah, if you would have set those two functions equal to each other, you would have got x equals 0, x equals 1, and x equals 2 for their points of intersection. Does that make sense?
And well, where they're equal, you always set them equal.
Right. To find out whether they're equal, you set them equal to each other. And most functions, yes, you're going to set them equal to 0. I'm sure there are exceptions to that. Like if it's an exponential function, then you're going to get the exponential on one side, a number on the other side, and like take the log of both sides. So it depends on what type of equation you have. If it's a trig function, you might end up with sine on one side, 1 on the other side. So it's hard to say, yeah, you're always going to set it equal to 0. It's just going to be determined by the nature of your equation. But you're going to set, to find their intersections, you're going to set f of x equal to g of x, and then just do whatever you need to do to find where those are equal. If they're polynomials, yeah, normally you're going to set it equal to 0 in factor, or use a quadratic formula. But if f of x was sine and g of x was a constant function, 1/2, then there's something else that we do to find out where those are the same. All right. So they give us several of those. Let's see. Occasionally, though, our functions are given to us differently. Well, let me back up. Sometimes we have graphs of things that are not necessarily functions. Let's suppose we have that. Is that a function? No. That's not a function. That's basically a parabola that's been turned on its side. And let's see. I believe that's x equals 4. I think. Y squared plus 4, is that 0? No. Y squared minus 4. So like here, y is 0. No. I'm making this harder than this has to be. Here, y is 0, so if we put a 0 in for y, we get x equals 4. If we put a positive 2 in for y, I think I just drew my picture wrong. What have I done? -2. Oh, this is a negative here. If we put a 2 in for y, we get 2 squared, so -4 plus 4 is 0. If we put a negative 2 in for y, negative 2 squared is 4, plus 4 is 0. So that's the equation that gives that graph, which is basically, if we were to put it in function notation, that's an equation in terms of y, where y is our input. And let's suppose they're intersected that with a line. Let's suppose we have a line something like that. And we want the area between those two curves. That area. Well, normally when we integrate, from a to b, the difference in our functions times dx, which in a sense represents a rectangle where the width is dx, the length is given by that. But notice, if we were to draw a vertical rectangle, in this region it's not a big deal. The length of this rectangle is whatever this equation is minus that one. But notice what happens over here. What is the problem here? On all of the problems that we've done so far where we got the area between two curves, we did the top minus the bottom to get our length. Well, if I call this f and this g, what function is on the top right here? If this is f and this is g, which gives us this value, which is on top right here? That's f. Well, what function do I have here? Isn't that the same function? We can't have that. We can't have both ends of our rectangle touching the same function. That's a little bit of a problem. What we can do, though, is we can take our rectangle and we can turn it. Notice anywhere we draw a rectangle in this region horizontally, it always goes from one function to another function, one function to another function. There's never a place where I can draw a rectangle in that region horizontally and both ends touch the same function, where if I draw a vertical rectangle, there is a place where both ends touch the same function. So if we have a vertical rectangle, the width is dx. It's the change in x. If we have a horizontal rectangle, though, the width is the change in y, so dy. When we integrate a function that has dx, then our function is a function of x. When we integrate with dy, our function needs to be a function of y. And I use the term function liberally, because it doesn't pass the vertical line test, but in a sense we can call it function. Notice for this type of function, our input is y. When we put a number in to that function, we put a 0 in, we got a 4, that was y. Our output then is x. So, real quickly, in terms of y equals mx plus b, this line has a y-intercept of -3, a slope of 2. But this is a function of x. We can rewrite that as a function of y by solving for the other variable. If we solve that for x, add 3, I'm going to do this down here, add 3, divide by 2, notice our variable is y, so that's a function of y. Let's call it g. So f of y, that's our red curve. G of y, that's our straight line. G of y, that means our input is y. When we integrate this, we're integrating dy, because that's the width of our sample element. which means that our limits of our integral need to be y values. When we integrated dx, notice our limits were x values, 0, 1, and 2. But when we integrate dy, so when we integrate dy, then our limits are going to be in the y direction. So whatever this y is to whatever that y is. Now let's come over on the other page and look at this. So for our first function, what was it? Negative y squared plus 4. For our second function, is it x or y plus 3 over 2? So if we want to find out where those intersect, we set those equal. We can get rid of the fraction by multiplying through by 2. So just multiply both sides by 2 so that those cancel. That's quadratic, so let's set it equal to 0. Subtract y from both sides, subtract 3 from both sides. Unfortunately, that doesn't factor. So we would have to use a quadratic formula for that. So it's the opposite of b, plus or minus the square root of b squared, minus 4 times a times c over 2 times a. So y is 1 plus or minus the square root of, that's 1, what's that, 40? So 1 plus 40, so 41 over negative 4. So whatever that comes out to be. So 1 plus the square root of 41 over negative 4, and 1 minus the square root of 41 over negative 4. Now, normally the book's not going to give you problems that are this messy, but I just wanted to illustrate, okay, how do we find out what these two values are? Now, if we calculate those, this is actually the lower one. I don't know the x value, but the y is 1 plus the square root of 41 over negative 4. Here, the y value is 1 minus the square root of 41 over negative 4. So if we set up our integral, in the y direction, we're going from the lowest y to the highest y. And we're going to take the difference in the functions. Notice, if we take the difference in the functions, in the x direction, it was the top one minus the bottom one, which was the largest value minus the smallest value. Here, if we're looking for the largest value minus the smallest value, would it be the left minus the right or the right minus the left? Which way is a larger value, to the right or to the left? Right. So it'll be the function on the right, which is f, minus the function on the left, which is g. Now, typically you're not going to have to go do as much as we did. We actually had to come up with our functions because I made the picture up. Normally they're going to give you the functions. They're going to give you f of y and g of y, and we have to find out where these points are by setting them equal to each other, and we're going to have to find out which is on the left and which is on the right. So basically, we go from the lowest y to the highest y. We're just going to sketch two functions, or two curves. If we're doing dy, it's going to be the one on the right minus the one on the left. Always notice what variable this is. Whatever variable this is, that's what your variable is in your integral. Also, whatever variable is, that's going to tell you what variables or what numbers to use for your limits. If this is y, these are y values. If this is x, these are x values. All right, let's take a break there.